Let's look at numerical representations of functions, specifically with tables. So first, we want to just determine whether or not a table is a function. And what we want to keep in mind with functions is that for every input, there's exactly one output. So does each x value have exactly one y value? Or even in a shorter way, you just need to be careful of repeated x values. So, for example, with this first one, if we just look at the x values, they're all unique. There are no repeats, so this is a function. Because for every input, there's exactly one output. So we have these outputs. It doesn't matter that there are repeats in the outputs, that's fine. You can see the y values over and over again. What we can't have is the same x values. Whereas with the second table, what I'll notice is I see x equals 1 and x equals 1. So I have two inputs there, and they map to different outputs, and that's not okay. So this is not a function. So for every input, there should be one output, and in this table, there's too many. So if you're looking at a table and need to know whether or not it's a function, just check out the x values. If there are repeats and the repeats go to different numbers for y, then it's not a function. Sometimes tables will be tricky and say this was actually a 0 here, then that would technically be a function because it's just repeating the value and it's going to the same output, but that's not the case here. So with that, we're going to stop using that second table there, so I'm just going to scratch that out so I don't accidentally use it. Okay, if the table does represent a function, find the following. So f of 1, what that's going to be is it's telling me that x is equal to 1, and I want to know what is y. So what's the output when x equals positive 1? So with that, I'm going to look at x equals 1, and its matching output, which is that positive 1 right there. So f of 1 equals that f of x value of 1. So that would be the solution. For the second one, it's telling me x is equal to 6, and it wants to know what would y be. So for this one, I want to look at x equals positive 6. So if I look at my table here and look at my x values, what I'm going to notice is I don't have a positive 6. So from this table, that's an undefined value. We don't know what it is. So I'd say f of 6 is undefined. Another way that we can look at the tables is solving. So f of x equals 1. So in this case, it's telling me what the y value is, and I want to find out what is x. And sometimes there's one solution, sometimes there's multiple solutions, sometimes there's no solution. With these cases that we just looked at, you should just have one output, or there could be the case where there are no outputs. But this is reversing it, and it's the idea that we can have multiple y values, a y value that go to multiple x values. So what that'll look like is I want to see where does y equal 1 on this table. Well, we have there, there, and there. So there's multiple possibilities here for x. X could be -1, it could be +1, it could be +3. So that's what I'm going to write out. X is -1, 1, or 3. And we could just list them out. For this next one, solving f of x equals 6. So we're saying y is equal to 6, and we want to know what is the x value that goes together with that. So looking across my y values, I'll notice there isn't a 6. So with this one, we would say there is no solution. it doesn't show up on the table, we can't solve that equation. Let's look at a word problem with tables. So the following table gives values for I equals M of t. It's showing the number of Americans with internet access. So that's our value for I. And that's in millions. And then t is t years after 1950. So let's look at M of 45 and how we would interpret that. So M of 45, so t equals 45, that equals 40. So where I'm looking at here is t equals 45, and the output would be 40. So t equals 45 is 45 years after 1950. So that's translating to the year 1995 right there. Then this output of 40 is in terms of number of Americans with internet access. So this is 40 million Americans. So to put a sentence together, what I'm going to say is in 1995, 40 million Americans had internet access. Solve M of t equals 172. So in this case, it's giving me my output value. So what I want to use is this 172 over here, and the fact that 55 lines up with it. And this is a case where there's only one input that works for it. So we find that M of 55 equals 172. So kind of same process as I did up above there. So 1950 plus 55. So this is going to be the year 2005. And this 172 million Americans. So making a sentence, I'm going to say in 2005, 172 million Americans had internet access. All right, and then one more piece with average rate of change. So their wording there, this average yearly change, so this average change is that AROC calculation, and we're looking from the years 2000, so that would be t equals 50, to 2005, which is t equals 55. So what I want to look at is M of 55 minus M of 50 over 55 minus 50. So M of 55 is that 172, and then minus M of 50, which is the 113, over 55 minus 50, which is 5, and then plugging that into a calculator, we'll get 11.8. So some pieces I want to take note of. Again, we need to make sure we talk about this as an average. The change in X, they kind of outline it for us as we're looking from 2000 to 2005. We're seeing an increase here because it's positive rate of change. And then the amount of change is 11.8 million Americans. So putting that all together, I'm going to go ahead and say between 2000 to 2005, the number of Americans with internet access increased by 11.8 million on average. So that gets at all of our pieces. We mentioned the average, mention the change in time, that it's an increase, and by how much.